Yeah. So this Cadence tool actually works on a Linux platform. So this operating system which you are seeing here is a Red Hat Linux, which is installed in our lab at CBIT. Okay. So let me show you how to start with that, how to launch Cadence. So before we begin to launch the Cadence, okay, what we do is we try to create a folder, because so what we'll be creating a lot of files in between, and whatever files we create, we want them to be at a safe place. Okay, so for that I will just create a folder here onto the screen. How to do that is just to click, right click on this, create a folder. I can give it a name. Okay, so once I'm done with this, I'll go into the folder. Yeah, the thing is, in order to launch this particular tool, it is not graphical user interface, a button like click, which is going to launch it. Even though for some versions it is there, but for this version, what we have, it needs to be, what do you say, launched using commands. Okay, command line interface. So I need the terminal for typing my commands. So what I'll do is I'll just right click on this and open a terminal. Okay, so once I have a terminal here, okay, so I will simply run a command called a csh. Okay, csh is a command in Linux operating system. Okay, it is C shell. I am actually activating C shell because this command, whatever is written, this what do you say, application, whatever is written is mostly in C language. So therefore C shell I need to activate. Okay, once I am done with that, not visible. Okay.
Yeah.
Uh, Yeah, so as you are not able to see the terminal, let me again start with the terminal here. Uh, yeah, so this is the terminal which I have launched. Okay, so in this terminal, let me clear it.
Continuation.
Clear.
Source.
Okay, what I'll do is I'll end this and try to create another.
CSH.
Yeah, I hope now you're able to see this window, the terminal window. Yeah. Okay. So what we do here is we simply type this CSH. Okay. CSH is a command in Linux to activate C shell. Okay. Shell is actually an interface where you can type your commands. Okay. And C shell means it activates C language commands. Okay. So once it is done, we then uh, open this file called as CSHRC. Okay, so CSHRC is actually an environment setting file for Cadence. Okay, so it will set the required environment for Cadence, and it, in other words, opens whatever the tools are there in Cadence for you to run. So as I have clicked that, you can see welcome to Cadence tool is the what do you say, message I have got in my terminal. And now Cadence has a lot of different tools. Okay, so but we will be actually working on Virtuoso. Okay, so I will be launching Virtuoso just by typing Virtuoso here. You can see here Virtuoso, Virtuoso. Just click on this and Virtuoso will be launched. Okay, if you are unable to see this, let me uh, share it again. Yeah. Okay. So now you can see this Virtuoso has launched. It is there here below. Okay. Right. We will not go into the details of this. Okay. So now once you have this Virtuoso, okay. So how we create is we actually create libraries. So if you can just explore this, if you can just go to file. Once you click on file, there are a lot of options given to you. One is new, open, import, export, refresh, all those things you can do. So generally the files here are arranged in the form of libraries. Okay. And again, in libraries, they are divided into cells. Okay. So let me just open a new library for my design. So I will simply write new library. So whatever I am doing on this computer, I will be storing it in my own library. Okay. So let me call that library as some test one, or else my one, my library one. Okay. So here what I will do is you can actually create a new technology file. Okay. And you can reference to an existing technology library, or you can attach to an existing technology library. And this you cannot do anything also. That options are there. We will go with attaching the library, because I want to design circuits, and for designing the circuits I want the MOSFETs which are already built by the what do you say, the fab lab. Okay. So whatever fabrication lab has provided me with the MOSFETs, I will use those MOSFETs and try to design it. Okay. I am not going to create a new fab lab for myself. So just click on that attach to an existing library and click on apply. Okay. So once you click on apply, it will give all the list of existing libraries to which you would like to, what do you say, attach your file to. That means which technology you would like to work on. So you can see we have the options for 45 nanometer technology, again 90 nanometer technology, 180 nanometer, for, like this different technologies are there with me. So I am interested to do with 180 nanometer. I am not going to do any hi-fi design. Okay, just 180 nanometer technology is enough for me for explanation purpose. I'll just take that and click on okay. Okay. So once this is done, I will simply close this by clicking on okay. Yeah. So now you can see the library is loaded. GPDK 180 nanometer library is loaded, and it is ready to use by my library, that is mylib1. So your design library mylib1 is successfully attached to technology library GPDK 180. So now what I do, once I have my library, I will try to create a new cell, because the designs here in Cadence, they are called as a cell. Uh, and cells, you can create a cell view for your cell. Just click on this cell view. Okay. And you can give some name for this cell view. I will call it as inverter, because I'm trying to design inverter. I will call my design as inverter. I mean, I will attach to my library. You can see it is already attached to mylib1. Okay. So just click on okay.
Yes.
Okay. So some warning messages you will get.
Yes.
You can click on this okay and proceed. Once everything goes well, you will see this window popping, and this is what is Virtuoso. Okay, so this is actually, again, Virtuoso has a lot of windows here, lot of graphical tools you are going to have. This tool is actually called as what do you say, uh, schematic editor. Okay, so you can actually edit your schematic here. You can create your circuits here use in this particular tool. Okay, so apart from this, there are many tools. You can see if I just click on launch, it gives me a lot of different options: ADL, Excel, GXL. So these are all other tools which I have. Okay, so some tools are for simulating your designs, some are for doing layout for your design, like this for creating what you say, symbols for your design. You have another tools. So like this, many tools are there. But the basic tool which we are going to use for our explanation today is going to be a schematic editor, which you are seeing here. Okay, so I would like to create an inverter. Okay, what would be an inverter looking like? Okay, so an inverter would simply have an NMOS. Okay, so it would be simply having uh, a PMOS here connected to VDD, and then you have the drain of this PMOS connected to the drain of another NMOS. Okay, okay, and then you have their gates connected, and this output is taken from here. So this is my output terminal, this is my input terminal. Okay, so this is what I'll be designing. So this is a PMOS transistor. This is an NMOS transistor. So I just need a PMOS and an NMOS transistor and need to connect them appropriately, provide appropriate inputs in order to get the results. Okay. Yeah. So for that, as I said, I need an inverter for me. So you can just go and see this symbol. So you can see there are a lot of options here. Many options are there. We are not going to look in detail. When we design it, you will come to know what are these options for. Okay, so some basic options like opening file, new file, all those things are there. And in order to save, so like this, some options are there. Let us not go into that detail. Just click on this, create instance. Okay, so I want a MOSFET for my design, one P MOSFET or an N MOSFET. So that you have to select from the library which we have just now attached, the GPDK library. So once I click on this, I get this window. Then go and select the GPDK library, 180 nanometer, uh, GPDK 180. So all the cells in this library will be listed here when you click this drop down. So you have all the different transistors, but I am interested in a PMOS transistor. So just click on this PMOS. Okay. And it is asking me what should be length of the PMOS transistor, width of the PMOS transistor. You can see because it's a 180 nanometer technology, the length is minimum length is fixed at 190 nanometer, and you have the minimum width fixed at 2 micrometers. Okay. So there are some minimum dimensions which you cannot go below that. This width can be reduced, but there are some an extent to which it can be done. Okay. So then there is something called as fingers. I think most of you know what is a finger. If you don't know, just wait. I will show you what is the width of that. Okay. So like this, once you done that, okay, just click on hide. Come here and place the transistor. So our PMOS is placed here. Yeah. Anyone trying to say anything? Yeah. So, okay, so PMOS is done. So I would like to now see my NMOS. Select one NMOS. So for that, again, you go into instance. Okay. Okay. So here is my window. That is why I'm unable to see this. Let me close this window and get back to the design. So here, when I click this, again, this window comes here, and I want an NMOS this time. So I will simply write NMOS, or you can simply click on this drop down, select the NMOS. NMOS is here. Okay. And then you can hide it, place the NMOS here. You can see P for PMOS, the arrow is in inward direction, and for NMOS, it is in outward direction. So this is the source of NMOS, this is the source of PMOS. Now we need to connect them. For connecting, this is the wire. Just select this wire, connect it appropriately as required. Okay. Right. This is body that needs to be connected to the source here. And this is the body terminal that needs to be connected to the source. Right now we are not going to have any body issues, so we have to connect the body and source, short the body and source. Now our inverter design is done. What is left over is the, what do you say, the power supply. So for the power supplies, what I will do is I will again go to this library. This time I will not go to GPDK library because that is for transistors. My power supplies will be present in analog library. Just select analog library. Once you click there, you will have different uh, elements present there. I want my power supply. VDC will be written here. DC supply. Okay, so just click on that VDC and just specify what is the voltage you will be working at. So we'll be working at 3.3 volts because it is 180 nanometer technology. Just 3.3, you can write that. Click on hide. Yeah. So I have my VDD. Okay, so let me connect the VDD to the source of the PMOS transistor, and this I'm connected to the source of NMOS transistor. I need to ground this also, so that I need a ground. So again, I can go into this library and select ground. So you can simply type here. If you don't want to waste time, just write ground, GND, ground comes. Okay, just take it. And one ground, another ground also I require, so I'll just keep it here. Right. So with this, I have given the power supply. Now what is needed is I need to give some input to this. Okay. So in order to check whether it is working or not, so again I will use a DC power supply. This time I will not use a DC power supply. Instead, I will go for some pulse source. Okay. So V pulse. Let's go to V pulse. Okay, a square wave I will try to generate. So voltage 1 is 0, voltage 2 I want 3.3, a high voltage. The period of this, I will say that the period is 10 nanoseconds. Okay, and rise time, fall time, need not mention that. Pulse width, okay, so if period is 10 nano, I want it to be a square wave. So therefore 5 nanosecond I need to place here as the pulse width. So once you are done with that, just keep that source here. Okay, you can wire them up. Right. Now I need to check my output here. So for output, you can actually put a label. Just click on this and you can place here. Name I will write it as output. So I will name that wire so that it becomes easy for me to identify it. And this I will call it as input. Right. So just save my design, check save my design. Okay. Check save is going to see whether any errors are there or any connections you have missed, that it is done. So once it is done, now I need to simulate this design. Okay. So, and what type of simulation I need to do, because I have given a time domain input, I need to see the time domain output. So a transient simulation would be enough for me. Okay. So for doing simulation, I need to launch the tool ADE XL. I'll go with this. Okay. Yeah, IDL is enough. Okay. Yeah.
Not Excel.
Yeah, good. Okay, so this is actually simulation environment. You can see it's a different tool which actually is used to simulate circuits. So for simulation, you can see a lot of different things are there. Design variables. Our design doesn't have any variable right now. Analysis, what type of analysis you want and what you would like to see in the waveform, that you can select here. So right now, let me choose an analysis for this. So analysis, in order to choose that, you can just go to this analysis tab present here. Click on this, choose. Okay, so I need to perform a time domain analysis. So I will select transient. And because my time domain signal is varying for 10 nanoseconds, so I would like to see some 5 cycles of that. So 50 nanoseconds is enough for me to end my simulation. So I will end my simulation at 50 nanosecond and just click on OK. Okay, S is not required. Yeah. So once this is done, then what I would like to see, where I would like to see the waveform, which waveform I would like to see, that is depending, that depends on your output. Okay, so that outputs you can select here. Okay, outputs to be plotted, select on the design. Just click on this, it will take you to the design. So I want this to be plotted and I want this to be plotted. So I've selected both the wires which I want to see as output, which I need to be plotted. So I've just clicked on that. Again, I will come back to my tool. You can see those two are listed here. Once this thing is done, you can start the simulation by clicking on this green button here. Okay, so once I click it, the Cadence starts creating netlist for this, checking errors, and then it starts doing the simulation. Once simulation is done, I have my waveform here. You can see these are the waveform which you have got. Okay. So here you can see it is actually quite confusing. So what I will do is you can see in the left side, in is represented in some this red. Both are almost in the same color. So what I will do, I'll try to change this color. Just click on this waveform. You can, whatever you click here, it will be highlighted. That is one thing. Okay, so you can see like this. You can differentiate, or if not, you can change the color by right clicking on this. Go to color and let me give a yellow color for the input. So yellow color is the input and the red color is the output. So let me just highlight both of them by selecting both of them. And let me zoom into this by zooming like this. Okay, so this is the waveform of your square wave. Okay, so if you want thick lines, that also you can do. Okay, type, you can go and change the type as continuous line, styles, solid. So it shows you as a solid line. Similarly for input also, you can give the style as a solid line. Uh, yeah. So here I have my input and output. Further zooming, yeah, you can see there is some delay in between. If I would like to run this circuit for at a further lower time period or higher frequency, this would create a lot of issues. But right now for this, it is quite easy for me to simulate. So this is about the transient analysis of the waveform. Let us say if you want both the waveforms separated, then you can click on this button here. As you can see here, this thing. If you click on this, both the waveforms will be separated and you'll be able to see, you can see input is here, yellow color, and this is the output. Just invert. That is what is an inverter, right? This is the zoomed version. If you want, the entire 5 cycles, you can just play with this to get different this thing. Okay. So once you have seen this, once you have satisfied yourself with the simulation, you can close it. Okay. Come back to the design. Okay. And you can save this. If you want, you can save this setup also. You can just click session, save state. This, if you can just save state, if you click, you will get this option. Okay, so it will be saved as state 1. So next time I need not enter this thing. This will be ready-made coming. It will be coming automatically if I select the state 1. Just click on OK. Right. So now I can get rid of my simulation. This thing. What you have seen just now is a time domain simulation. And there is one more thing I have discussed. Okay, so apart from inverter, we are interested in its IO characteristics. So if input varies from 0 to VDD, how is the output going to vary? That also we would like to see. Okay, so for that, you need to change input and you need to see the output. So that is actually a DC characteristics, not a time domain or a AC characteristics. Okay, so for that, okay, what I'll be doing is I'll be simply clicking on this. Okay. For this, I'll be again launching my simulation, launch ADEL. Again, my simulation environment opens up. Now I want to do a DC simulation. So I go into analysis and I choose a DC simulation. You can see a DC option is visible here. So I'll go for that DC simulation. Once DC is selected, then you are actually trying to change some DC voltage. In our design, there are 2 DC voltages. One is for VDD, another for VGS. So what you would like to change, that it asks. Okay, so it is asking what should be changed, what should be the sweep variable, whether it should be temperature, design variable, component, or any other parameter. So I want a component parameter to be changed. Whatever component we have placed there, one of the parameter of that should be changed. Just click on this. Okay, and go and select the component. We go here and we select that the VGS we are trying to change. Okay, input voltage, which is here, gate voltage. So this is selected. Okay, so once you select that, again, you can see that V1 has come here. V1 is the name of that source that is already selected. Now parameter I need to write. What parameter in that source I'm interested in? So if I go and select this, on the left side, you can see a small window coming in. So there the parameter name, that is the DC voltage parameter, is this thing. Okay, so I need to select this DC voltage. Okay, once you double click on that, you will get this. Let's select this DC and click on OK. Okay, so your DC voltage of V1 I am trying to change. Then what should be the range I would like to change? Okay, whether it should be changing from 0 to 1 or 0 to 2, that you have to decide. We will change it from the lower potential to the higher potential. The lower potential in our design is 0, and the highest potential which we are using is VDD. What is that value? 3.3 volts, right? So we'll keep that. Okay, and sweep type automatic, you can actually select this how you want to sweep. Okay, let it be a linear sweep. Step size, again, let it do it for a very fine value, 0.01. I'll simply write say apply and okay. So DC simulation is selected. Then what I would like to plot, again, and that I need to select, go to outputs, to be plotted, select on the design, output. I only want to see the output. Let us say if you want to see input also, just click on this. There's no need, because that will be coming on x-axis, right? So I've selected that, just run the simulation. So Cadence is simulating. Now once simulation is done, now you can see the characteristics. So this is my output. This is the output varying. When I vary the input on the x-axis. So x-axis showed my input variation, and the y-axis shows the V out values. You can see here for you can see for V in equal to 1.25, output also is 1.25. So this is the point of what do you say, the you can say the center point, or the quiescent point for this particular circuit. Not quiescent point, we are not setting any quiescent point, but this is the point. If the circuit hangs because of any reason, it is going to hang at this voltage. Okay, that is the importance of that particular point. Okay, is it okay? The characteristics, you can see it is far more different from what we have done earlier in other tools, because the here the models are going to be more realistic. So more realistic diagram you are going to get, right? Yeah, I will save this setup also. I'll just go to session, save state. Now this time it will be saved as state 2. I need to write, because state 1, if I write again, it will erase my previous state. Just click on apply. Okay. Let's close this. Right. So I hope you are able to get what I'm saying here. Just give me a second. I need to just clarify one thing. Is Isha in the meeting?
Yes, sir.
Yeah, okay.
Yes, sir.
Yeah. Yeah, please ask me. Any doubt you are having? If anyone is having any doubt, please ask me. Right. Your classmates have joined, Isha?
Yes, sir. They have joined.
Okay, right. Thank you. So let me proceed in that case. So we have done with this particular changes. Okay. So, but the thing is, generally, we don't want our circuits to look like this. We'll generally try to hide our designs, or we would like it to be as small as possible. This is just a small circuitry, so you are able to see the transistor, and it's quite easy to wire them up. But if it's a complex circuitry, the wiring becomes very difficult. So for that, what we do is we will be first interested in generating layouts for them. Okay. So if I want to generate a layout for that, or create a symbol for this particular thing, how would I do that is, for creating symbol, the first requirement is you should not have any power supplies here. Okay. So you can just get rid of that. You can have it also if you want, but mostly we'll just omit them. Uh, yeah, we'll. So this is our circuitry. Remaining thing voltages were just for testing purposes. Okay. So this is actually what will be present on the IC. Okay. Not even the ground. Ground also will not be on the IC. So if you want to create a symbol, yeah. Yeah, please don't annotate. If you annotate, it is getting problem here. Yes. Yeah. Yeah. Message. Yeah, please, because you have drawn this, can you please arrange it? Please arrange it so that I can come back to my screen. Right. Thank you. Yeah. Yeah. So let me just go back. Uh, yeah. So we were here. Okay. So now in order to create symbol, what we will do is we'll first create this thing, pins for that. Okay. So for that, you can simply click on this pins and give some name. One pin I require for my input. So I will call it as in. Direction is input. Okay. So once it is done, you can bring and connect it here. One pin I require for output. You can simply click on out. I'll simply write out. Okay, hide it. Okay, direction I need to change. So out, it's an output pin. Okay. So if we change the direction, their input output, their direction changes actually. And then I can create one more pin for VDD. Yeah. So this is going to be my power pin. I'll use it input output for this. Right. Keep it here. And one for ground. Ground input output. I'll keep it here. Okay. So once you have kept this design, okay, you can again check save it. After you do it, if you want to create what do you say, diagram for this or a symbol for this inverter, you can simply go to create. No. Okay. You can click on create and then cell view. From cell view, you can just create a symbol. So you can see it is again creating a new cell with the name inverter. It is creating from schematic and it is creating in a new cell view called a symbol cell view. Okay. So for that, a new app is going to open or a new window is going to open. It is not going to be in the same window. Okay. So it is just asking me whether the directions are correct or not. Left, I want input pin. Right side, I want output pin. Top pin should be VDD. Ground, I don't want on the top. Ground, I want on the bottom. So you can just cut from there, paste it here in the bottom. Okay. Just click on OK then. As you do it, it opens another window. So this is another, what do you say, a layout app, layout tool for Cadence. So here you can work with different layouts. You can design layouts for yourself and all those things. So this is the layout it is creating for me. So this, it is, my inverter is going to look like a rectangle if I go into place this. But I don't want it to look like a rectangle. I want it to look like a triangle. So you can change the shape. And this red color boundary is a boundary which is just to keep other components away from your design. Okay, if anyone is going to come place another component, let us say resistor, just close to here in this particular region, it is going to give a warning. Okay, so this red color indicates the boundary where other components can be kept. I don't want this boundary, and also I can simply delete that. So I'll delete it. This instance name is, let us say if they are creating inverter 10 times, the inverter 1, inverter 2, inverter 3, like this 10 times, it is going to give different names. That names is going to be visible like this. If you want the names to be visible, just keep it here. If you don't want, you can remove this. I want my names to be there, so I will just keep them there. Okay, so now I am not interested in this design, in this diagram. I will just delete it and I will try to create a, what do you say, a new design for me. I want a line. I just create on this create line and then you can draw whatever you want. Okay, so I want a triangle here. Okay, so this is going to be my inverter. Now what I need to do is I need to place this component. So I will simply drag them so that they get connected, or else it is going to be look very odd, right? So this, delete one line. Yeah, so this is the output. Put its name, I can keep it here. This is VDD, slightly here I will move. Then I will move this component so that it comes in contact. Okay. This.
ఆ విండోలో వస్తుంది, ఎర్రర్స్ చూపిస్తుంది కదా ఆ విండోలో.
So this I will place it here or else, and then I will drag this. Right, this is my VDD. Same thing I'm going to do with the ground.
బిల్డ్ చేసాక ఎర్రర్స్ వార్నింగ్
Yeah,
చూస్తాం.
can you please mute yourself? Someone. Okay, so input I'm placing here. Yeah.
హలో.
So this is going to be my symbol. Yeah. Anyone having any doubt? Yes. So this is going to be my inverter. Whenever you are going to place it, its part name is going to come here. What is going to be the part name is, it is the same name which you have given in the library. Okay, so that is name is going to come here. And instance means, let us say if it's a first instance, u1, u2, u3, these kind of names automatically pop up. Okay, so this is going to be my symbol. I am going to simply save it. Just click check save. Okay, with this my symbol is saved now. So now I will try to make the same circuit, but this time I will try to use my symbol instead of this circuit. Okay, so for doing that, what I can do is I can just create a new file from here. Just click on new file and then new. So it takes to me to the library. In the same library, I would like to create a test bench for inverter. So I will write test inverter, a new schematic, and click on OK. So you can see a new window opens up. In this window, I would like to not place any transistors. Instead, I would like to place the inverter which I have designed in this window. In this window, whatever inverter I have designed, that I want to place here. I will not place this entire circuit. Instead, the symbol what I have created for that circuit, that I will place here. How to do that? Again, click on the schematic. Okay, once you have clicked on that, just go to this time. Where is the inverter symbol present? Inverter symbol is present in our library. Okay, so just go in and see my library name is mylib1. So I will go to that library, just click on inverter, and I want a symbol for that. You can see the symbol is already coming here. Just click on hide, come and place it here. Okay, so your inverter is placed here. Now I can give all the power supplies. You know how to give them. Go to the analog library. Analog library and VDC, DC voltage. Okay, and we need one more voltage for signal, therefore V pulse. Okay, and V pulse what we have given, first voltage 0, second voltage 3.3, and this time I would like to give a even lesser pulse width. Okay, 1 nanosecond let me give, and the period I will give it as 1 nanosecond, and pulse width is just half of that, 0.5 nanoseconds. Okay, so because if you run at very high frequencies, then only you will get to know what is the problem with the circuit. Okay, so that is why I'm trying to give a very high frequency signal, and I need ground also for my supplies. So just click ground here. You can simply type ground, it will come. Just click on that. Yeah. Right. And one more ground I need here, right? So I will copy this. Right. Now I'm wire them up. VDD, connect here. This ground is connected here. This ground is connected. Input voltage V pulse. Output voltage I would like to see. I would like to give it a name. Out. Okay, just keep it somewhere else. Here I have not given any voltage values, so double click on this. You can, or else instead of double clicking, you can single click this. On the left side, all the parameters will open up. You can go through that parameters and change. I want to change the DC voltage. I want to give a 3.3 volts here. So 3.3 you can give, and just press enter. That is enough. Yeah, you can see VDD has come there. So I'll just save this. Check save. Here are the warnings. Okay, so it is because of this wire. There is no issues. Okay, it is okay only. Or else if you want, you can omit this by creating a pin, an output pin you can create. if you don't like that error, or else if you keep it also, no issues. Just check save it. Now it is okay. You can see. Now I will test this design. How I will test the design? I will launch the ADEL tool. Okay, analog design environment tool. ADE stands for analog design environment. Okay, L is all those numbers, versions, and all those things. So again, I will go for simulation. I want to see a transient simulation. Analysis. Choose transient. But because my source this time is frequency, a time period of 1 nanosecond, so 5 nano would be enough as a stop time for me. So I'll just click on OK. It has come here. Outputs, what I would like to plot. I will just click on this pin and my input pin here. Right, I'm done with that. Now you can run that by clicking on this green button here. Yeah, you can see here. This is again the diagram which you got. Again, if it is not clear, you can change the colors, or you can change the type to solid if you don't like it. Input, again I will represent with a yellow color so that I can make the difference. So now when I zoom into this, you will see all the issues popping up. Okay, earlier design or earlier simulation was quite ideal. Okay, wherever you have this 1, you are getting a 0, but this time you can see there is some delay. Okay, so here input is going from high to low at this point of time, whereas output is rising after some time, and it also has a glitch here. Okay, so this glitches and this delays is because of the parasitics present in your MOSFET. Okay, and this you will not be able to see if you use some other tool. Okay, it will not be properly displayed, and that is what is the what do you say beauty of Cadence, that all the details, realistic details, it is going to show you. Okay, so you can see all the spikes. So in the industry, what they will do is the ones they will simulate this, they get all the spikes, and then they will think about the mechanisms how to remove this spikes. Okay, they will come around, they will try to design some techniques and all those things and get rid of these things and try to match it as ideal as possible. We are not going to do that in this stage. Okay, right. Okay. So I'm happy with the simulation. Yeah. Okay. One thing I would like to do is I would like to see them as two different signals. So you can see input is on the top, output is below. If you want to see multiple cycles, just zoom out by using this button. Multiple cycles. Okay. I hope you got it. So let me stop this. Okay. So once you're done with this, okay, I will save the state one. Characteristics. Okay, let me go to the characteristic simulation. Okay, how I will do that? Again, I will go with IDEL. How did I simulate characteristics? I go for analysis. What type of simulation? It's a DC simulation. No one is responding in the meeting. Okay, DC, again component parameter. So what component I will be requiring? Just go to this. Input is here. So I would like to change my input DC voltage. Just click on this. It will show this window. Just select the DC voltage. Click on OK. Okay. So it already comes here. V1 DC. I'm trying to vary. From where to where I will try to vary? From the least voltage to the maximum voltage, 0 to 3.3. And what type of sweep I want? I want a linear sweep. Let us say 0.01. Very fine values. Click on OK. Yeah, come back to the window. What I would like to plot, outputs to be plotted, select on the design. This is the output I would like to plot. Okay, right. Once that is done, come back, simulate. Yeah, so this is the characteristics again. Okay, this is the same characteristic because the circuit is same. No, we have not changed anything in the circuit. It is the same circuit what we are using. Okay. Now, what I would like to do is, we know that this characteristics actually, if you have studied the design of inverter, okay. So in the design of inverter, it is up to us. We can change this characteristic. We can move this characteristics here and there. Okay, let me show you the characteristic first of all. Yeah, so this characteristics, if you don't want it to rise here, that means it is actually changing at 1.2. I'm not happy with this 1.2. I want the characteristics to be on this side, right side, or to be on the left side. Okay, so that means I want a more noise margin on the higher voltage side. and lesser noise margin on the lower voltage, output lower voltage size, then that I can do by moving the characteristics here and there. Can anyone say me how I can do that? How I can move these characteristics here and there? Design of inverter, I think you might have studied. Okay, so in the design of inverter, where will be this line? The ratio of the transistor Kr is equal to root of Kr is equal to 0.5 VDD minus VT plus VTP divided by this equation. You might have studied if you have already studied, or if not also it's okay. You will study this in the theory. Okay, so what is the equation? Root over Kr. Kr is actually the ratio of Kp, Kn by Kp. Kn is nothing but mu n COX of NMOS transistor. Kp is mu n COX of PMOS transistor. This is equal to 0.5 VDD plus VTP, threshold voltage of PMOS, divided by 0.5 VDD minus VTN, threshold voltage of NMOS. Okay, this is going to happen at midpoint, at the midpoint or at the transition point. This is the or at the threshold voltage of transistor, at threshold point of transistor. Okay, so I got that. I was actually missing that particular word. So this word, where is that? Where is that? Here. Yeah. So when you plot, okay, instead of this, if I plot, input also, we have seen that these two, input and output, were intersecting at a point. Okay, so this point of intersection, you call it as threshold voltage, threshold point of inverter. Okay, threshold voltage of NMOS is something, threshold voltage of PMOS is another thing. This point is called as threshold point of inverter. This point where both the this NMOS input and output are what do you say, intersecting each other, you say it to be the threshold point of the inverter. Okay, so the threshold point of inverter, at this point, it should satisfy this particular equation. What was the equation? You can, it has to satisfy this equation. Okay. Okay. Okay, the whatever equation I have written just now. Right, it should satisfy that particular equation. So now I can actually move this line here and here, because it all depends on Kr, I said you, and Kr is nothing but it is a ratio of Kn by Kp. And Kn by Kp can easily depends on W by L ratios. Okay, so therefore W by L ratios of NMOS and PMOS can be changed to get these values. So for doing that, what I will do is I will just do same simulation DC I will use, but then I will try to see the effect of this simulation when I change the width of NMOS to some value and width of PMOS to some value. Okay, so how to do that is by doing parametric simulation. You can go to simulations, not simulations, yeah, tools, parametric analysis. In the parametric analysis, you're supposed to have a variable here. Okay, so let me add a variable because we have not created the variable, we will not be able to do that. So let us first go and create the variable. So how to create a variable, let us just see. Okay, I'll just keep this thing aside. Let me call it as state 2. Okay, I'll just close this. So where is that variable present? Variable is, I have to make the width as variable, because changing that is going to change my characteristics. So I will go into this inverter design. How to go into that? Just click on this, right click, and say descend to edit, descend edit. Okay, so when you descend to edit, it actually gives you this particular thing. So in this thing, what I will do is, to the NMOS transistor, I will go into the design of this properties, its width was 2 what do you say, micrometer. So what I will do is, instead of keeping using one finger of this, I will use W finger of this, okay, or N fingers of this. What is a finger? I think you will be knowing. If you don't know, please contact me some other point of time. I will say you what is a finger. Okay, so let me call it as N. N is a multiple actually. So whatever width is there, that will be multiplied by fingers in order to give you total width. So finger width into number of fingers is going to give you total width. So my total width is not going to be 2 micrometer. It is now going to be 2 into that means this N. It is going to be 2 into N. Okay. So just click on apply. Okay. So now the width which was originally constant, now I have made it a variable by taking this N. And what is this N? This is my variable, design variable. Okay, so let me give the design variable. I will come out of the design. How to come out of the design is using this up. Okay, so you can just click on this up. It takes you to this design. So now when I launch the ADEL, let me open the earlier state, whatever I have session which I have saved, load state, state 2. So my state 2 comes here. Now this time I have design variables. So what I will do is simply I will say variables and copy from cell view. So whatever variables are there in my design, that will be coming here. And there is only one variable N which has come here. Initially I will keep this variable N equal to 1 and I am going to simulate. So if N is equal to 1 into 2 micro, it is going to be 2 micro, no effect. And the same design you are going to get. Yeah. Check save. So I have to check save the design. Then I have to simulate this. Any warnings I'm getting here? Okay, right. So the problem is I did not save my edits there. So again, I will go there. I will save the this edits by clicking on check save. Then I will come out of the loop. Again, I will check save this. Then I'm supposed to run the simulation. Yeah, you can see it is the same design which you got earlier. Same yellow blue. Okay, right. Same point, it is 1.2 volts. Okay. So now what I will do is this effect, I will try to see the characteristic if I change my W. What is going to happen to this characteristic if I change the W? So in order to do that, we have to do parametric analysis. So go to tools, parametric analysis. Variable is the width, and variable I have used is N. So just click here, N will come. Okay, and I want to sweep it from 1 to, let us say, 4. What is going to happen if I change from 1 to 4 or 1 to 3? Let me say 1 to 3 in the steps, total steps of 3. Okay, so once I have done that, check save this. Okay, no need of saving. You can just click on this green color. It will simulate. Okay, once it is done, you will get this characteristics. Okay, so as you can see here.
और कितना टाइम लगता है सर? और कितना टाइम?
10 minutes. 10 minutes.
1 निमिष.
Okay, so you can see the way effect of changing the widths. Okay, so by changing the widths, it actually comes down. The threshold point of the inverter is varies. So what is the threshold point? Okay, it is the point so below which you get logic 0 and logic 1. Okay, so any input voltage below this is treated as logic 0. Any input voltage above this is treated as logic 1. And this is the point where it changes. But there are a lot more details are there about inverter. I'm just talking at a very high level. Okay, I hope this is discussed in your classes, especially for MB students. I think this is discussed in detail in the class, but this is how you visualize it. I'm trying to simply visualize whatever you have studied. Is it okay? Is it okay? I need response, please.
Yes, sir.
Yeah. Right. So that is what is all about the inverter. Again, in order to design this, you have a lot of equations. You can calculate that KR, whatever I have said, root over 1 by KR is equal to whatever is that equation, you can use that equation, put different values in that, obtain a value of Kr, obtain a 1 W for NMOS or PMOS, fix 1 W. In this design, what did I do? I fixed the W of PMOS. I did not change PMOS W. I only changed the W of NMOS. Similarly, you can also fix the W of PMOS and change the W of NMOS. So let me do that. Let me do that. Okay. So I will again descend into the, let me close this simulations, parametric, uh, this thing. Let me close that. ADL also I will close it, but I will save this as state 3. Okay, so what I will do is I will show you what is going to happen if you change the W of PMOS. Okay, just go descend into this, descended it. Okay, you will get your circuit. Here I will just go into properties. Yeah, properties. And here I am going to change my N. I don't want any variable here. I want to fix this. Just click on 1 there. Okay, so once you click the 1 here, you can see width is fixed here. Whereas here also it was fixed. So now I want to make this as variable. So instead of fixing the W, I will go into the properties. And yeah, here again I will use N fingers for PMOS now. Okay, apply. So now this width has become variable, whereas this is fixed. Okay, I have to check save this. I have check save the design. I will come out into a hierarchy. I will check save this. Again, I will try to launch my simulation ADL. Okay, I have saved the session. I will try to open my session number 3. It is saved as. So click on 3. Okay, it has come here. Now I will simulate it directly. Yeah, so as you can see, this is the characteristic which we have only for a single value of W, when W is same without changing. Now I want to see what is the effect when changing, after changing. Okay, so how to do that? Go for parametric. Okay, just go to your design simulation environment, go to tools, parametric analysis. Okay, so once you are in parametric analysis, select this variable. N is the variable you have. Change it from 1 to 3. Okay, I want total 3 steps. So once I simulate it, yeah, you can see how the characteristics shift. Okay, they shift towards right side or on the higher voltage side. Okay, it is obvious, right? If PMOS width is going to be large, it is going to produce more current and it is going to dominate. And for PMOSs, we know the threshold voltage is going to be on the higher side. So therefore, the characteristic itself shifts on the higher side. That is as straightforward as that. But different textbooks explain in different ways. Okay, so you can just, so we have seen how to move these characteristics here and there, and that is what the design of a inverter is all about. Okay, so when anyone says you to design an inverter, it is not just placing the transistors there and giving them whatever the output you get. Okay, it is all about changing these parameters in order to get the characteristics what you desire. Okay, this is what is one of an example. So like this, there are many things which can be done on inverter, like power consumption is there, like you have the rise time, fall time, how to get good rise times and fall times. There are some techniques for that. Okay, so anyway, it will not be possible for me to cover all those things. So as discussed by sir, or as requested, sorry, instructed by sir, I have shown you the effect of this thing on the design of inverter. Any other thing you would like to know, please let me know. If was some other time we will like to see that, we will see that. Okay, I hope it is understood. uh, Anyone, you can respond. Is it understood whatever I have explained here? Any doubts you have, please let me know. Yeah, Yeah, Isha, is it okay? Is it okay, Isha?
Yes, sir.
Okay. Any other things you were expecting in this? Any other simulations you were expecting? I think you have done this in lab. Have you done this?
No, sir, not yet.
Okay. Okay. Okay, then. This will be the end of our session. Thank you for being patient and listening to this particular thing. I hope this will help you in your projects and in your, what do you say, the courses. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.
Right. Yeah. I'm ending the meeting now.